Continuing on to today's presentation, it's going to be experiencing the power of 4- and 5-axis machining in CAMWorks. So kind of our general overview agenda today is we're going to discuss a quick review of automatic feature recognition, what it is and the benefits of it, discuss knowledge-based machining with a general overview of what it is and kind of a little bit of how it works, and then how these two features can be used to help automate and speed up your programming process, even in the 4- and 5-axis realm of machining. So that's kind of our goal and question today, is just to see the power and how quick and easy these two features can be used to ease the programming of complex stuff on 4- and 5-axis. And then there towards the end, we'll do a Q&A session. So that's kind of our general overview. The first thing I want to talk about is a quick thing here on automatic feature recognition. I think it's one of the main features of CAMWorks, to where we have automatic feature recognition. So the CAMWorks automatic feature recognition can be used to speed up the programming process. So it's a speed to help automate your programming. It will interrogate the CAD model, being a part mode or assembly mode, and find the prismatic features of the machine, thus saving the programmer from time and telling it what to machine. And here's an example part up here of some of the features that it will find automatically and create them for you. So the goal is this: if it can create them automatically, it saves mouse clicks to speed up programming. So you can see it'll find, like circular bosses, circular pockets, irregular pockets, fillets and tapered pockets, countersunk holes, irregular bosses, or rectangular boss, irregular slot. And an example as I'm walking around this part here, rectangular pocket, counterbore holes, and they can be in different orientations. It'll pick up different setups there. The odd brown pocket, corner slot, multi-stepped holes, odd brown boss, rectangular slot, tapped holes, and holes. So that's kind of a general overview of the features that it finds automatically with the click of a button. Will it find everything on your part? No, especially the non-prismatic ones, and that's times where you can put them in interactively. So we'll do both of those today, but we want to show you how quick and easy it is to create some features and how the automatic feature recognition can simplify the programming process and really speed things up, even in the 4- and 5-axis area. Okay, the next main key feature of CAMWorks that we're going to talk about, of a key tool we're going to utilize today, is the function called knowledge-based machining. Okay, knowledge is power. That's kind of the most powerful feature of CAMWorks, in my opinion. So knowledge-based machining or rules-based machining, the two different terms are out there for the same type thing, is the key to automating your CNC programming process. In my opinion, it's the best tool in CAMWorks, and yet the most underutilized. It can really reduce programming time and simplify programming and help standardize your programming. Okay, let the software remember those things for you is kind of our concept here. This is all done through the CAMWorks Technology Database, or TechDB. And what that does is this stores information about your machine, materials, speeds, feeds, tools, and all the different rules for your machining process. Okay, and essentially it assigns defaults for all different scenarios. Okay, and that's what creates the automation and really speeds up your programming time. Is it remembers the settings for you and defaults to those parameters for you, so you spend less time trying to remember what settings are and entering settings and running the operation parameters and machine kinematics and that type of stuff. So you'll see a lot of that done today, and so it's beneficial to teach CAMWorks your programming techniques. It'll greatly improve your programming process, and that's what we're going to show you. Some of those stuff I'm going to demonstrate here coming up is going to have stuff that's already been taught into the database to automate the programming process to help simplify things. And that's done simply with a save operation plan, or opening up the TechDB and reviewing the TechDB ID number and changing the fields manually. Obviously, the most easiest one to do that is the save operation plan. These are all techniques we teach in other webinars or in our training classes We won't get into teaching and modifying them today, but we'll just do a general overview of kind of how these features can, illustrate how these features simplify and improve your programming efficiency. Kind of a general overview here of knowledge-based machining, kind of how it functions, kind of deep diving in here, because this is, like I said, one of the most underutilized one, is just to kind of shed some light under the hood here on things, is when you create the feature, or if it's done interactively or automatically, it is a feature type, and there's all different feature types. So the knowledge-based machining is a database that sits in the background, and it identifies what the feature type is you're machining. Okay, because you're going to machine a pocket different than you would a hole or something. So it's got to know the feature type. Then there's different strategies. And there's a drop-down list here of all the different strategies you have. You can create your own custom strategies, name them anything you want, which is very beneficial, especially if you have families of parts or things that you machine frequently. It's nice to have your custom strategies. And I have some of those that you'll see as we program here today on some parts of some custom strategies of how they can save you some time. So when it's looking at this with the database, it's going to look at the feature type, the strategy. Then it's going to look at some details of the feature, such as if it's blind or through, and if it has a bottom radius or not. So this will be different here based off different feature types, but there's different details of that type feature. Okay, and if you notice, there's an ID number next to one of those. And that's because, just there, because it's a different feature type and a different strategy and the different details of the feature, it's going to have a different ID number. And different ID numbers will output different operations and different operation parameters and tools based off that ID number. But kind of continue on here in the feature conditions, it looks at more than just the details of the feature. It also looks at the stock material. Granted, this one here that I'm illustrating is shown for all materials. You can have different cutting strategies and default ID numbers for different groups of materials, such as an aluminum group versus a tool steel group, etc. And if you are on a lathe, and it'll have different strategies if you're on a main or sub spindle. But the other one is the feature size, because the features are different sizes, you would machine them differently. So you can break it up at different sizes. This example here is kind of wide open to capture all type rectangular pockets, because the size of it is between 0 and 1,000 inches. So this is a generic one, no specific size range here. But you can break that down to all different sizes and make it have different operations that will output down here, which you'll see down here on the operation type. So every different feature condition ID will have can have different operations and different tool selection criteria and different operation parameters. So for instance, this one right here, ID 599, which is a rectangular pocket with a rough finish strategy that's blind, any material type on the main spindle, and pretty much any size between a 0 and 1,000 inches. It's going to output and default to a rough mill strategy and a contour mill strategy or operation, which kind of makes sense with the strategy name and rough and finish. And then it's going to, how does it pick the tool? There's all different ways you can do that. There's some formula settings right here to pick your different tool. You tell it the tool type up there, such as this is set to a flat end mill. And you can tell what turret it's on if you're doing mill turn. If it's on a turret 1, 2, 3, or 4. You can use math expressions to figure out the size tool, or you can use a static tool and tell it what tool to always use for that feature ID condition. This one is set to use a math expression to where it'll use 0.4 of the largest inscribed circle, which is the largest circle it'll fit in there, and then it'll be times 0.4 of that. So it'd be basically 40% of that inscribed circle. And the upper range would be 0.75, so obviously 75%. So it'll find a tool that fits between there that's in your tool library or tool crib and select that tool. So it allows it to more intelligently try to pick a tool based off the size of the feature. So that's kind of the concept with that. And then after that's done, you can have different operation cutting parameters. And if you click that icon down there in the database, it'll open up all the different operation parameters, the same you see in your program in CAMWorks, and you can change those different parameters. So this allows you to have completely different rules or operation parameters based off of different information of the feature. If it's, like I said, if it's what type of feature, the strategy, material, the size, and so on. So that's kind of a background of how knowledge-based machining works within the TechDB. Okay, and then we're going to kind of just see some of this stuff in action of these tools and how they apply into programming. So we're going to kind of jump right in here. Some of the two main parts we're going to focus on today. We're going to do some 4-axis stuff here on a tombstone. I'm going to show you the power of automation there with automatic feature recognition and rules-based machining, how quickly and easily we can program this 4-axis on all 8 of those parts. And then over here we're going to do one on some 4- and 5-axis preposition and simultaneous on this guy. So that's where we're going today. And we're going to go ahead and switch to SolidWorks and CAMWorks. So I'm going to go ahead and open those up. As you know, I'm running SolidWorks 2020 here with CAMWorks 2020 added as an add-in to it. And we're going to go ahead and grab our 4-axis assembly here. And I've got these set up in my design library here, so we're going to go ahead and pull those right out of it. So I've got my assembly opened up here, and you can see this assembly is configured on this tombstone, which will be 4-axis. It's going to rotate around like this for a 4-axis horizontal mill. And we've got this part in here 8 times. So we're going to program all 8 of those on a 4-axis tombstone. You can see I have different features here through my assembly. I have the part in here 4 times, and I have a model of the stock as well in here, and that's because I'm going to have this stock already kind of squared up in that perimeter machine on a pre-stage before we hit the tombstone to mass produce these out by getting all the details in that one face setup that you see. Okay, so you'll see a bunch of holes and stuff like that in there. That's what we're going to focus on. In my CAMWorks data, I do have a coordinate system in here that we're referencing to identify how the rotary axis is set up and configured for defining the machine kinematics. So we're going to go ahead. We reviewed the assembly here. I'm going to jump over here to the CAMWorks side, which is the CAMWorks feature manager here. And we're going to open this up to define our machine. And this is one of the advantages of knowledge-based machining in the TechDB is you can set custom machines in here with different feeds and speeds, maxes and stuff, and CAMWorks will alert you that. As you can see, I have different machines set up. We're doing a 4-axis horizontal mill. You can make that as specific and call it whatever you want by, if it's a Haas EC series horizontal or whatever it would be, DMG, Mori, it doesn't matter. You can call it whatever you want. I'm not trying to favor any tool manufacturer, so I just have a generic one here in my database, just called a 4-axis horizontal mill. So, but to kind of illustrate that, I picked that mill to activate it. It's going to default to my favorite tools, which you can also set in the database to help speed up programming. And that's my tool crib of my favorite tools that I most commonly use. And you can even default given station numbers of what those tools would typically be in if you wish. Different controllers will default to post-processor, so I simply have that defaulting right to the post-processor when I pick the machine. The posting tab has stuff you can set up that's kind of a little more custom. But the big one is, too, when you set up your 4-axis machine in the database, you can tell it if it's 4-axis, what the rotary limits of it are is nice to have, and you can make it default to which axis it rotates around and which direction is positive. So these are all parameters if you set in the database, by clicking one button, you set all those automatically to help speed up your programming. So that's what I have done. So that by picking that one button, I set all those parameters automatically. So we're going to go ahead and OK that. So we've got our machine here. And then in a parts manager, this is here out of SolidWorks because we're in assembly mode. We've got to tell it what part we want to machine. And I've clicked a part and it's added all of it here. So this part is same part is in here 8 times. That's why you see 8 instances of the same part. Okay. And then we'll come in here to the stock manager, and you can go through here and assign different stock types. Okay, so you can have, bounding box, CAMWorks offers extruded sketch, STL, reference another model. I'm doing the reference on another model because, as I said, those were pre-machined out here, to make us flat, so you can sit up there. So all we're doing is a secondary operation to machine everything in that front face. So the perimeter has been machined, and those have been machined to thickness. prior to being put into the tombstone to kind of just knock these all out real quick. And you can have different stock shape for every different instance here. If I click different parts, I can have different stock definitions. Okay? And of course, you can pick different material types, etc., out of the list here. So I've got those all set up as far as identifying what I want to machine or what parts I want to machine in the assembly and what machine type I want to use. So now we're going to start identifying things to machine. And this is where things can be done automatically or interactively. And we're going to do the extract machinable features icon here. We're going to click that icon. And what that's doing, that's running the automatic feature recognition I talked about earlier. You can see it's initializing the automatic feature recognition module. So that's interrogating the model or assembly and looking for things to machine on here. Okay, and I always suggest reviewing them here. And I want to point this out, since this is the same part 8 times, that's why there's different sections in the tree here in assembly mode. This one part is what it found everything on here, and then this is each rotation around the tombstone of those 8 parts. This will be for, if I click that, you can see how it's doing both in this setup direction, 1 and 2. So it sees, even though there's 2 in that same setup direction, it's going to get both of those. So as I identify my features on the one part, it's automatically put them down here because there are multiple instances of the same part. So that really helps speed up programming that intelligent stuff here. So I'm going to go ahead and just kind of review these and discuss some of the features it found here. I found an ob-round pocket automatically. You can see the highlight here, the green highlight. If I covered over it, it's blue. So it found that ob-round pocket, and it defaulted to a rough finish strategy. You can make different features default to different strategies, to whatever strategy you use the most, which helps speed up programming time. That's another rule in the database you can set to save machine time. Here's our regular pockets. There's 4 of them, the automatic feature recognition found. It found this irregular slot, which is everything around there with a bunch of islands in it. It's got that circular pocket. It found these tapped holes, and because they're identified with a thread callout here in SolidWorks, if the CAMWorks was able to read that thread callout, determine it's a 448 UNF hole, so that's what it's going to default to pull that proper 448 tap and drill tap, etc. Same thing with the 1032 tap. Found these counterbore holes and these counterbore holes, and it found this hole through the center here. So I like to kind of review see everything it found automatically. And if I wanted to change that, I can, or I can add features interactively, etc. But I'm looking at this. I'm actually going to change that because I want to show you guys how to change it, and it'll change it for all instances. This hole right here is how it found it, as if it's going to machine this pocket first, then drill the hole. I want to actually may want to drill this hole first. I want it to start above the pocket, then come all the way down. So I'm just going to go ahead and edit that and tell it to start at the top of the stock, so the highest level, so that the hole feature is drilled from the top down of the material, the stock, or the part, instead of from the bottom of the hole through the part. So when I change that, and that would automatically change all those down here. Okay, so now I have all my features identified here. I'm going to go ahead and hit Generate Operation Plan. This is when the knowledge-based machining kicks in. It's looking at that TechDB for all the different rules that are set for this feature type, that strategy, this material, and that feature size, just as I illustrated in the presentation earlier there. It's looking at all those things to determine what operations it outputs, what tools it picks, and what those cutting parameters will default to. Okay, to kind of quick show you here, I'm going to go through, and then my next step in programming is we're going to put some work coordinate offsets in here. Assembly mode, you must assign your work coordinate for you, so we're going to go ahead and just use G54 for everything. So I'm going to go ahead and assign that to each part. You can make it different work coordinates per part if you want. I'm just going to keep it kind of simple today with just G54 kind of everywhere for my work coordinate 0 point. Okay. So I'm going to go through here and do that for all those setups, orientation, because I can have different ones for every rotation if I want. I'm hitting the assign button. You can see here it's assigning 54 for that part instance 1 and 2 of that orientation. And then this is the last rotation down here. We're going to do the same thing. Okay, so we've assigned our work coordinates, kind of my next step there. And then when I'm programming and assembling with multiple instances, I like just to go ahead and generate the toolpath real quick for one orientation, not all of them yet, just so I can kind of proof it, because it's going to kind of do the same thing on the others. So if I can start finding and checking things, I like to simulate and go through some of these here just right off the bat of keeping it simple. And these aren't optimized yet. It's going to simulate one feature at a time. So we're going to rough that one, then we're going to finish that. Then we're going to rough this one and finish in that. We'll come back and put these in a more efficient sequence. You can see it's using tool 12, then tool 13, back to 12, then back to 11. We'll resequence these here in a minute. But I like to just kind of debug it one feature at a time because it's easier for me to process and verify things mentally. And so I just kind of have my technique that I use. So I'm going to go ahead and hit the simulate toolpath, and you can see all the different parts here. Oh, notice it doesn't show the tombstone or anything yet. It's because I identified only the parts machine. I haven't identified what my fixtures are. So I'm going to go ahead and back out of that, and we're going to identify what our fixtures are so that we can see them in our simulation. So I'm going to go ahead and pick that tombstone here. And by the way, I right-click on the first mill part setup, and in this any setup, you can identify what your fixtures are. I'm going to go ahead and grab the jaws here and hit add all instances. I'm going to grab the center one there for the hard jaw, add all instances of it, and that part, add all instances of it. And my Windows is dinging, and that's kind of loud. Sorry about that, guys, when I had those. So now we're going to come back and simulate this already set up, and you'll see that we see all of our fixtures and our parallels and all that stuff. So when I've got collision checking on, I'm just going to kind of let this run and kind of run through these one feature at a time and see if there's any collisions or anything like that and check for. And whoa, it found one. It got this nice loud alert from CAMWorks. It found a rapid collision on the contour mill 6 between the tool and the stock. So we're going to go investigate that and stop the simulation. It's contour mill 6 that told me, and it says there, and it's where it's at right here. I'm going to go look at this, and that's because all that lead in, lead out is kind of hitting the side of the part. So that tells me we need to adjust our lead in, lead out location. The tool path is pretty good, I think. It's just where that lead in, lead out is occurring. So we're going to change that a little bit here and go right in that corner like that. So I like that. Okay. And then I'm going to come down and check that on all the different ones here and the different rotations. I'm like, oh yeah, we're going to go ahead and change that in this rotation. And this is kind of why I like to do one setup at a time, and that way I can go through and get a quicker idea of where things are going before I start optimizing things. I'll go ahead and go into here, edit that operation, just changing that point. I'm picking the segment that I wanted to lead in. And I can hit preview, you guys. You can also hit F5, which automatically regenerates the tool path, which is the same as the preview button. Okay, so that's another way to do it, kind of a tip and trick there. So you can either hit the preview button to regenerate the tool path or the F5 key. So I'm going to change that point here, we zoom in, there we got it, the blue dot moved, and I'm just hit F5 on my keyboard, and that regenerates the tool path, aka previews it. I'm going to go ahead and OK that. So that went through and fixed that issue in every instance. We're going to kind of go back and simulate this again on just that first setup and see if we got anything else going on here. So you can kind of see this guy run a little bit here. Again, I'm just checking it again to make sure there's nothing I need to adjust. Oh, between 17, that's a little bit different. I don't know what that one is. I'm not sure. I'm not seeing what that one is. I'd have to read that again. I wonder if it's a tool shank or something, because I'm not seeing a tool path. We're going to go ahead and I want to show you guys generate tool path for everything. And we're going to go ahead and sort this operations once we have all the tool path for everything here. Now, when I say generate tool path for everything, it's doing all 8 instances and all the different rotations. Okay, so I have tool path for everything. And then we're going to go ahead and sort them, operations, because as I mentioned, these are doing rough mill, contour mill, tool 12, 13, 12, 11, 12, back to 11. We really want to set these, and while that one tool is up, to do everything, all the different rotations, then change the tool. So we're going to go ahead and tell CAMWorks to sort those. So I'm going to right-click on my machine definition, go to Sort Operations in the Sort tab, or like I said, in the process, here, buying across setups. That's going to tell it to consider optimize between different setups. So that does the rotations first, then tools. Right now, you can drag and drop these around. I'm set to do all the drilling operations first. Remember, I want to do the drilling first with that big hole, drill the hole through there first. And then we can say by tool, and then size, hit apply, and you can see how it organized all the tools. We're going to hit and hit OK. You can see how I did the center drill here, then the one down there, and then while that same tool is up, it's going to rotate over to this orientation and get that top one, bottom one. Then the next one is going to rotate to this side, grab those, and then it's going to come around and rotate over. I'm going to rotate the part so you can kind of see the tool path here. It's going to get those while that same tool is there, and then that one down there, and it's going to start, well, it's on this same setup, it's going to switch the tool, do those, and it'll start going back in an alternating fashion and kind of come back, work its way around. So you can see how we are simulating, or only we'll see it simulate, but you can see kind of here in the tree how it's doing all the different rotations with the tool there. So we're going to go ahead and simulate that. Again, you see that here. We're going to go ahead and hit play. And you can see the rotations here. You can see it milling around. Right now it's doing B0. If it was real fast rocking back and forth, that was the different rotations. You can see it just indexed there to B90. It's milling. I'll mill all around these parts here. Okay, let's take a little bit of time to simulate here. I want to go a little bit more. But you guys can kind of see how the simulation and automation, for automatic feature recognition and rules-based machining kind of kicked in, and I quickly got some tool paths on these parts and programmed them, and it's done simulating. Okay. We'll go ahead and OK that. So we got all those done right there. And then, of course, we're going to post some code and send it out to the machine. So, of course, nothing's complete without code. That's kind of unnecessary. So we're going to go ahead and post this out. So we're going to post-process that because we've got to have code or we can't make parts. I'm going to let this post out here. And then CAMWorks, you can open the G code in the NC editor if you want. I've got this set to run in machine simulation. I'm going to go ahead and just open this up in machine simulator, which is an additional option that you can purchase in the CAMWorks bundle to simulate the machine simulation. There's definitely an upcharge for that type process, and it's got a model of all the fixtures and all the tooling, and so you have to have a lot of that stuff done, tool holders, and the entire machine, and write all the kinematics. This is kind of a more advanced setup and stuff, and of course, it's an upgrade of the bundle, and it's got a marked up on the price for it to accommodate for all the bells and whistles on this. But it is kind of neat to see. So I'm going to show you how that would function here on the 4-axis, and it's going to simulate the actual G code. So I'll go ahead and OK that. Just finish post-processing, and it's going to go ahead and open this up. Here, and you'll see our posted code. I'll kind of scroll through that. Here's our code to program and run that part. And you can see it here on the simulator. We've got our nice CAM's basic horizontal mill here set up to kind of mock that. And we're going to go ahead and kind of peek through here and go ahead and hit play. And we're going to let this start running the program, and you'll see it kind of move around. We can zoom in. You can see that guy index different rotations to drill in those holes. And we're going to do a trick here that every operator wishes they could do to make things easier to see. We're just going to get rid of the enclosure on the machine. I know that's not part realistic, but every operator wishes they can until they get a nice coolant shower. But yeah, so it makes it easier to kind of debug and see the program run. So it's kind of a neat feature, but definite upgrade. So you can see it's simulating the G code and it's drilling the different holes. And you can check the rotations out, so etc. So we'll get into some of the milling here, just for you guys, so you guys can see it because it's drilling some holes yet. As I said, recall we did all the drilling first. There's a big through hole. Doing some of the countersinks on the holes. We spot drilled some and drilling them yet. Now we're tapping some of the holes. And we're getting in some of the milling now. Milling that pocket out there. And yeah, you can move this around too, and I can get different views and whatnot too. And this will alert me if I have any collisions or anything like that too. I can zoom in, you can see it milling those pockets out with a volume mill and starting to hit those, etc. That's kind of how that works, guys, and you can see we're simulating the code with the 4-axis code. So I hope that kind of shows in the 4-axis how the automatic feature recognition and rules-based machining can be used to speed up programming even in complex detailed parts with multiple parts in the 4-axis realm. I'm going to go ahead and pause this for sake of time and stop this one. We're going to go ahead and move into the 5-axis one. And we're going to go ahead and open up our 5-axis part. Assembly here. And as you can see, I have an assembly here. I got my part. I have my stock, and then it's set up on this fixture here. Fixture plate, and this has been basically turned down on the lathe to be round the size, and it's had this slot moved in the pre-op and the bolt hole so we can bolt it there, so we can set it up on this fixture, riser fixture, and then machine all these different channels in here on the 5-axis tombstone type machine. So that's kind of our goal here. Kind of rotate it around. You can see how we're going to get some geometry around here and these chamfers, all that type stuff. We're going to all do those 5-axis mix of preposition and simultaneous. So kind of show you how that works with knowledge-based machining to help speed that programming process up. Again, I can jump over here to CAMWorks. I have a 5-axis machine. I have just a 5-axis trunnion I called the mill. This is the default, I select it. It's going to grab my favorite tools, my 5-axis post processor. Just sets all this machine kinematics up for me, so I don't have to set these every time. So it's got the rotary axis limits, the tilt axis limits set, that type stuff. And that's critical here, the tilt axis, because you don't want the part to tilt back and smack the back of the machine. That's why they can only go one way so far versus towards the operator versus away from the operator. That's why there's different limits, and different machines have different limits. So different machines that have different defaults, and it's tough to remember what those are. Look them up once, set them in the database, and let it remember for you. It's always going to rotate the rotary axis around the Z, which is the C axis, and the tilt axis is around the X on this trunnion machine, so that'd be the A axis. So we've got that set up by picking the machine, and so that knowledge database kicked in and set all those machine kinematics for me, so I don't have to remember those. Because if you get one of them wrong, the 5-axis code will be wrong. It won't run on a machine. So it's nice to have it set right and it remember it and default to it when I pick the right machine. Again, we're going to parts manager tell it what parts you want to machine, because this is assembly mode. We're only going to do one part. That's this guy here, not our fixture plate. We want to machine the part to cut, not our fixture. So I've got that selected, and then I can define my stock for it, which is another model here. As I said, it's been turned down on a lathe. Got some material on the top face, but it's got that slot channeled through it and the bolt holes in it, so it can be mounted to the fixture to machine all the 5-axis stuff. So this is a secondary operation to machine the rest of this part complete. Okay. You can do extract features if you want. I'm going to put some features in here manually just to kind of walk you through the process of that to show you how easy it is to do them manually, and we'll put some in automatically as well here. So I'm going to go in here. I'm going to insert my mill part setup, and I want to do facing first to face mill that off. So I'm going to go ahead and I want that tool to come in like that, and that's going to be a different rotation there, because if you see that arrow, that's the tool axis approaching, and that part's got to tilt at an angle to face mill that back and forth. So whatever I pick that face, CAMWorks is going to calculate what that angle would be from the 0 point that I defined in my machine kinematics. Okay, then I'm going to tell it what I want to machine. The feature that I want to machine is going to be a face feature type. I'm just going to go ahead and pick that face right there on the part. It's going to go out to stock for me automatically by default and up to stock. So it's going to kind of highlight what I want to machine there for my face mill. I'm going to go ahead and OK that. And then I'm going to insert, oops, that's my fault, wrong mouse click. Another mill part set up coming straight down to machine these slot and holes. I'm going to go ahead and hit OK here. And that creates that different setup, and that's a different rotation. That would be a 0 rotation because it's straight down. Okay. I can right-click on it and hit Recognize Features. That's another way to invoke the automatic feature condition to where it will only find features in this setup direction automatically. If I hit Extract Features up there, it finds them in all setup directions. So we'll hit Recognize Features, and it found the counterbore holes. Those are the prismatic features in that setup direction. It didn't find the slots because it's not a true prismatic feature, because the top face isn't flat. It's at a different angle to that setup. Okay, so that means I got to put those in interactively. I'm going to go ahead and define those interactively here. So I'm going to do a slot feature, pick that face. It found that automatically open air edge. That's what that dashed line is. That's their segment. And then it's kind of asking me how high to put it. That's why CAMWorks didn't find it automatically, because this face is tapered. It's not parallel with that. It doesn't know where high to start cutting things from. And I'm just going to go ahead and pick that point right there. Or I could type in a blind depth, and that gives it the kind of the height of extrudeness of the CAM feature. And I can pick a cutting strategy. And you can see this is where you can have all different cutting strategies to pick from. If you remember, when the knowledge-based machining, I said it's going to look at different strategies to do different things. I want to rough finish it. So I'm going to do a rough finish, and it'll give me a summary here. It's going to pull a rough mill, the 1/2 inch in mill, and contour mill, which is a finish one with it, the edge with a 3/8 in mill. So I'm going to go ahead and OK that. I'm going to jump over here and do the same thing over here for this slot. Create that feature. Kind of go, I'm going to go up to this point because it's a little bit higher than that point because of the part of the feature. And we're just going to use that same rough finish strategy. Okay, that. And you can see how we're building these in the tree. I can drag and drop these around too, my features. I probably want to mill those first. And sometimes I like to try to keep my features corresponding to the operation tree. So I can drag and drop those around, put those first. The Then we're going to get in here to mill setup. I'm going to go ahead and use a preposition to rough this channel out here. So we're going to come in here and grab this angle here. I put a plane in ahead of time in there because I have a plane to pick, which is the same angle as what this feature would be, so the tool can kind of come in like that to 3-axis rough that out. When I'm 3-axis roughing this under a preposition state, on even though it's 5-axis preposition, it's going to clamp the rotary axis so it's more rigid for roughing versus doing it all simultaneous. So it's all simultaneous, the rotary axes are unclamped, so it's not as rigid, so you can't rough as aggressively. But I want to be more aggressive, more efficient, so I want to rough it as 3-axis, tilted at an angle so it's prepositioned with the rotary axis is clamped. Okay, and because it's prepositioned, it'll be clamped. So I did that setup. I'm going to go ahead and create that feature. To do that, I'm just going to go ahead and hit select all faces, and I can give it different strategies as we talked about here. And as I said, you can do custom strategies in the database. So if you machine something frequently with a technique that you use, let's say I'm always going to make different size grater plates, I want to have a strategy called rough grater plates in my database. So that's what I've created. So you can have custom ones in this list too. And that's one of the things you can capture in knowledge base to default parameters and capture that expertise I've learned over the years of making multiple grater rates. So I've got those parameters in there. So that's all saved in that strategy. I'm going to go ahead and OK that. And I'm going to go ahead and start right here because this is kind of the preposition stuff. Then we'll come back and put some simultaneous in at once. So I'm going to go ahead and generate operation plan. And I could keep going and put the simultaneous features in if I wanted. I'm just doing this to kind of illustrate things. So I got my different setups on preposition here. This is my different rotations. As you can see here, it gives me a summary. If I click that mill part setup, it says it's going to rotary axis going to go 9 degrees and it's going to tilt 5. Okay, to machine that tool path or that face. But I'm going to go through here and set my offsets or my work coordinate fixture offsets to the G54, and I'm going to assign it for that setup. And because I can have different ones for different rotations, I need to do that. So the same part at all rotations is just going to go ahead and use the same G54 work coordinate. So I've assigned those. Okay. While I'm at it, I'm just going to go ahead and edit my mill part setup. Go to the Fixtures tab. I identify that as my fixture part so that I can see it in my simulation. And I'm going to go ahead and generate toolpath for this guy, for all of them, so we can kind of review and see what it's doing here. 3-axis toolpath takes a little bit longer, so it's generating down here. You can see it in the CAMWorks Process Manager. I'll let that generate. Okay, so you can see I have face mill toolpath kind of going back and forth at that angle. Then it's going to come by and go straight to do straight down to the 0 tilt and 0 rotary. Let's just machine the slots and the counterboard holes and that type of stuff. You can drag and drop these any way sequence you want, or you can do it automatically as I showed you before. You can come into the operations and change them if you want. But I'll show you can just drag and drop these operations. Oh, I keep opening that. Sorry, guys. So something like that, or we can come down here. You can do them automatically or manually like I just did. So you can kind of hover all the different operations toolpath. You can see the area clearance roughed at. Like, oh, what's it doing? It's roughing some things that are already cut. That's because we need to turn on rest machining. I'm going to go into this area clearance operation, turn rest machining on, which it's on because it's my default parameter. But the rules base, it doesn't know all the different geometries of your part, because your part can change, your fixtures can change. You have to tell it what to consider from the rest machining. And that's what I'm going to do here by clicking that button. Is tell it, what are my other operations I want to consider everything from? I'm just going to do everything here. Hit OK. OK that and let it regenerate that tool path. And that should be a lot more efficient of roughing out those channels there, and not machine the areas that are already machined, such as the face and the slots, etc. So we have toolpaths just like that. I'm going to go ahead and simulate this just to get a rough idea of what it's doing before we get into the simultaneous stuff and kind of what it looks like. So you can see it faced it real quick, milled those slots, put the holes in, and roughed those channels out. Then we're going to come back and do some 5-axis simultaneous through the channel to finish those, the semi-finish and finish it. Then we're going to put some chamfers around this using some 5-axis swerve cutting. So that's kind of the end of my pre-positioned stuff to get everything roughed out and ready to go for the simultaneous. And we've obviously got stuff set up to do simultaneous stuff. I'm going to go ahead and do that from straight down setup. We're going to insert that mill part setup, insert a multi-surface feature because that's what 5-axis simultaneous uses. And we're going to go ahead and do that great. And 5-axis simultaneous identify only the faces you want to cut, not everything. And I'm going to go ahead and set my strategy. I have a finished strategy for my grater plates because, again, that's something I cut off often. So I'm going to take advantage of rules-based machining because I have a custom strategy that's got my cutting parameters set and tool selections that I frequently use to reduce programming time. So I'll go ahead and put that in. I'm going to do this a couple times here for each one of those channels. So I'm going to go ahead and pick that, finish that. Okay. And we got one more here. So I've got one for each one of those features across there. Okay. So then I'm going to put another one in here to do those chamfers around the edges. So I need a feature for that. So I'm going to kind of zoom in here. I'm going to grab that face, that face, that face. Make sure I'm careful and get just the faces. We want to do 5-axis swerve type cutting. So there's a strategy to default the parameters to do a 5-axis type swerve. Come over here and do the others here. I can go ahead and pick that first if I want. And then come back and pick the faces I want to machine. Okay. So I've got my features set up here for the 5-axis simultaneous portion, the strategies here. Now, it's very common in 5-axis programming to have to set up some guide curves. I did model that ahead of time. I have a guide curve kind of for each one of the channels, which is a sketch right down the center of those, and that's the guide curve the tool's going to follow, right on the center of that. And then I have a guide curve for the chamfer. I could pick the edges, but I put the guide curve in because I can do a chain select and just pick the sketch. I think is easier because I can create the sketch instead of going around finding every little segment because I miss one, then it won't follow the curve properly, or because I missed one. So I can pick individual edges or sketches. So I do have that set up ahead of time. And we're going to go ahead and generate some operation plans for the 5-axis simultaneous here. So that, again, that's looking at our knowledge-based machining and our TechDB to pick the default tools that we want to use for that 5-axis, finished 5-axis grate there. Okay. It pulled the right tools for that 5-axis operation. I'm going to go ahead and split my setup because I want to do these after I rough that. So I'm going to right-click and split my setup here and drag setup 2 down, and I'm going to drag all these 5-axis operations down. And then we're going to go in here, these operations, and pick our guide curves. So my knowledge-based machining set all the different parameters for me and defaulted them. I just have to pick my different guide curves because the thing that's not consistent is the different geometry between parts because it could have all different curves. So I can see all these different parameters are all set for me by my knowledge-based machining from pulling in the database. So I'm going to go here and reference my guide curve that I created, which is just sketch 1. To do that guide, I'm going to go ahead and repeat that process for each curve. So I'm going to have to do that 5 times because I have 5 different channels to cut 5-axis simultaneous. First one, and the 5th one. Okay, and I'll just go ahead and generate the channel one so you guys can see the toolpath real quick on those. So you can see I have toolpath for those. Doing multiple passes, looks like I'm doing 3. 2 semi-finishes, then a finish. This comes to depth, and we're going to do the simultaneous. I have to reference a guide curve to machine the swerve cutting around those to do those chamfers. I'm just going to reference a curve again, and once that curve, I could pick edges. Either one works. And again, I have that 5-axis swerve strategy that sets all these different parameter defaults for me, so I don't have to remember them. Let the software remember them for me to automate my programming process. That's the power of the knowledge-based machining. As you can see, there's a lot of different parameters in here to where it's much easier to let it remember them, default them to you to do 5-axis swerve cutting. We're going to do the same thing here to this next one. I'm going to go ahead and reference that guide curve, which is a geometry-specific thing. Right there. Okay, then I can go ahead and generate the toolpath for those. And you can see the 5-axis simultaneous toolpath to cut that chamfer and to cut that chamfer as well. One thing I like to do in 5-axis simultaneous is I think the step through is a great tool to kind of see things. You can kind of see the tool and the tool here, and those are the tilt curves, the vectors of the tool. You can turn those on or off. I kind of like checking those so I can envision what that tool is going to be tilting like going around that curve. I think that's one of the neat little hidden things, tips and tricks there for 5-axis simultaneous to check the tilt curves quickly, is to look at the step through, and you can do that from the step through icon right here as well, or you can right click on it and you can see the tilt curves for that guy. And you can also step through the tool path and play, get an idea what it looks like in the step through. So sometimes I like doing this for 5-axis simultaneous. And then there's the normal toolpath simulation you can do, which we'll go ahead and do that. Kind of orient the part here. It's going to rotate around Z and tilt around X. So you can see that's roughing that out. There's some 5-axis simultaneous there, and that was pretty quick. I think we're going to replay that and slow that down a little bit here. So you can see my face mill going across there, where it's tilted at an angle. I'm working that down deeper to get that face nice and flat, and then it's going to do those channels here. I'm going to bump this up a little bit. Okay. To drill the holes, pre-position, then this is the roughing of the channels here. I'll bump that up a little bit, and then we'll slow this down. There's the simultaneous going through the channel there. Get a kind of idea how that works. I'll bump that up, and I'll slow it down as it goes around the chamfer so you can kind of see a 5-axis simultaneous there on those chamfers. Okay, so we've got our tool path there. You can see how quick we did a lot of 5-axis preposition and simultaneous using both automatic feature recognition and the knowledge-based machining. And we're going to go ahead and, like I said, they're kind of not complete until you have code. We're going to post some code and send some code out there, because until without the code, it's just a pretty picture. So we're going to go ahead and post that out, get some code. And again, this you can open it in the G-code editor or in the simulator. I like to open up the simulator to show you guys here. Again, as I mentioned, the simulator is a virtual machine. It's an additional upgrade. But it's kind of neat to see the code run visually. So we have our 5-axis CAMS machine here that I built to simulate it on a trunnion. I have my code here we're going to run and simulate the G-code on. You can see it's got some of the preposition, and then when we get down in here, you can see the simultaneous, where it's moving the A and C axis. So I'm going to go ahead and hit play. You can see how it's doing the face mill operation, etc. There's the 5-axis preposition to rough out those channels. And then we're going to do the 5-axis simultaneous to do the channels to finish them. You can see the rotary and the tilt axis both moving there. And then when we do the swerve cutting, you'll really see the rotary and tilt axis move there. And that's when the things are real nice. You got to watch tool clearance and stuff on the back side and the top of this part here. And in case anyone was wondering, it would alert me and tell me if there's a collision if the back of this part were to hit the tool, the machine or something. That's why it's critical to model your machine and have this. This is, like I said, one of the more costly upgrades. A lot more work involved if you model your machine. And the more accurate you model your machine, the more accurate you can simulate it. And of course, when you're checking clearances, you want an accurate model of everything, your machine, your tool holder, etc. You can see the simultaneous there. And then that part is simulated.